Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss the equations of a line. So in this topic we will review the equations of a line. We'll then discuss how we can solve the system of linear equations to find a vector representation of that line. However, we will see that it is not in the ideal form. So instead we will describe an algorithmic approach that uses the cross product and the Moore-Penrose pseudo-inverse that algorithmically allows us to find that vector representation. Finally, we will discuss the differences between algorithmic and algebraic solutions to problems. Now, in R3, a plane is represented algebraically by a single equation. At this point in this course, you should immediately recognize what this is. A single linear equation in three unknowns. Consequently, if you were to solve this, you don't even have to do Gaussian elimination, as the augmented matrix is already in row echelon form, and therefore you'd probably assume, yes, there are two free variables. It is these two free variables that define a plane. There's actually only one circumstance where there are three free variables and consequently even infinitely more solutions, and that is when all of the coefficients are equal to 0 and d is equal to 0. In this case, every point in R3 is a solution. However, there's also a case where there are no solutions, and that is any situation where all of the coefficients are 0 except for d, which is non-zero. In this case, there are 0 solutions. These two we would probably describe as pathological solutions. Now in R3, a line is represented by a system of two linear equations. We're just going to assume that at least one coefficient of x, y, and z is non-zero for each equation, and thus ignore the two previous pathological cases. If these are non-parallel planes, then a line is the intersection of the two planes. So again, if we have two non-parallel planes, if they intersect, they must intersect along a line. Consequently, the above two planes define a system of linear equations, and the augmented matrix corresponding to those two planes is what we see here. From secondary school, you are aware that there are two possibilities. The first possibility is that the vectors defined by the coefficients of x, y, and z are linearly dependent, so each is a multiple of the other. What that means is, you'll recall that these are perpendicular to the planes, and therefore both of these represent planes that are parallel to each other. Consequently, the row equivalent matrix that is in row echelon form will end up looking like this. We will add negative A2 over A1 times row 1 onto row 2, and that produces this matrix here. It is in row echelon form. You'll notice, however, that there are two free variables, but the rank of the matrix is 1. So the only way that there can be solutions is if the rank of the augmented matrix is 1. If that expression is equal to 0, the rank of the augment matrix is 1. There are two free variables, and consequently there are infinitely many solutions. Basically, both of the equations describe the exact same plane. If that expression is non-zero, then the two equations describe two parallel planes, and parallel planes do not intersect. Consequently, there would be no solutions. By the way, before you worry about details, if A1 was equal to 0, you can then instead just move forward to column 2 or column 3, or swap rows 1 and 2. However, ultimately, the result will be the same. There will be 2 free variables, and only under very specific circumstances is there a solution. From secondary school, you're also aware of the alternative. And again, that is where the vectors defined by the coefficients of x, y, and z are linearly independent. Of course, you wouldn't have said it that way, but you would say that the two vectors are not parallel, and therefore they define planes that are not parallel. If the two vectors are linearly independent, you also know from this course there's only one free variable. That one free variable describes a line. All right, here we see two non-parallel planes. There is the line that intersects those two planes. Now, our goal here will actually be not only to describe that line, but also to find the vector representation of this line. So u perp plus alpha times a vector, unit vector, parallel to that line. Now, to find a vector representation of that line, you could solve the system of linear equations. So, for example, given the two planes defined by those two linear equations, we could write down the augmented matrix, convert that matrix into row echelon form, and then solve for the solution. Z would be the free variable, and so here we essentially have a vector plus Z times another vector. Well, this is in the form u plus alpha times v. Now all we have to do is normalize v and also to make u orthogonal to v. Problem: all of this, doing the Gaussian elimination, solving, determining the free variable, is not something that can be easily programmed. Consequently, we'd like to find something more algorithmic, an algorithm that would describe how we go from the equations to the vector representation. Instead, let's start with the vectors that are perpendicular to the two planes. So let's label these two vectors v1 and v2, and hopefully, given the previous topic, you know exactly where this is going. These two vectors are perpendicular to each of their planes. The line where the two planes intersect must be on the intersection of those two planes. Consequently, the line must also be perpendicular to both of these vectors. How do we find a line that is perpendicular to two vectors? We take the cross product and we divide by the 2 norm of that cross product. This cross product is perpendicular to both v1 and v2 and is therefore the only other possibility, the line that is parallel to the line itself. We now need the perpendicular vector u that lies on the line. That is the point on the line that is closest to the origin. So how do we find u perp? Well, we could try to solve the system of linear equations, set the one free variable to say 0, and then make that line perpendicular to the line v cap. However, there's a different approach. There's a construct called the Moore Penrose pseudo-inverse. And what it does is it maps a point back to a possible solution whereby that point is closest to the origin. All right. In this case, therefore, it turns out the uperp vector is simply found by multiplying the vector negative d1, negative d2 by this Moore-Penrose pseudo-inverse. That's it. And once again, this is something that can be easily programmed because it is a 3 by 2 matrix and it's a matrix multiplication. We're not solving a system of linear equations. We are just doing a very simple matrix vector multiplication. So for the example we just saw, we define the two vectors being the coefficients of x, y, and z for the two equations. We then assign v cap the cross product of these two vectors divided by their 2 norm, which gives us approximately the vector you see there. Finally, we calculate the Moore-Penrose pseudo-inverse, and we multiply it by the vector negative d1, negative d2, which in this case is now positive 4.6, positive 5.5, and that gives us that vector there. You will notice that v cap, if you were to calculate it, is indeed a unit vector, and u cap happens to be close to a unit vector, but it is not. It is the point on the line that is closest to the origin. You will also notice that if you calculate the inner product of v cap and u perp, that the inner product is indeed 0. Now, in this course, we are covering linear algebra. We're focusing a lot on the algebra so that it is clear that you understand the algebra behind all of the algorithms that we discuss. The properties, the null spaces, what's happening. However, when we are implementing a solution, it's often best to find efficient algorithms that solve the same problem. These algorithms can be easily written into code, and they can also be verified. Now, if someone told you what we described on the previous slide, it may not be entirely obvious that that's what's happening. However, that is the point of an algorithm. An algorithm is an efficient means of solving a problem, and it may be more efficient than, say, for example, doing the route algebra. Now, if you were to look at that matrix A, the pseudo-inverse of A, and you were asked to program it, you likely could. And therefore, you could also likely program matrix vector multiplication. Later in this course, we may be able to derive that matrix at the end of the course. Following this topic, you now understand the concept of equations of a line. You also know how to find the vector representation of that line by solving the system of linear equations, which has exactly one free variable. You understand, however, that there are more algorithmic approaches that solve the same problem, which we described using the cross product and the Moore-Penrose pseudo-inverse. You are at this point aware that in some cases, algorithmic approaches, while not perhaps intuitively obvious, can often be more easily programmed than algebraic approaches. This is therefore useful if you were to try to program this in, say, a microcontroller that is doing something that is actually in 3 space. Perhaps a vehicle that is moving or a drone that is flying through the air. Again, a drone has an orientation. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!